EC 111, lecture 13, set 9, we'll be talking about floating point numbers, which actually extend the dynamic range of the numbers that we can have by fixed number of bits. In this system, there is an agreement about what part of the number that we have, which is basically a number is a string of bits. And if you have a string of bits, then you could interpret it in many ways. It's really, as we have seen all along this lecture, it's really the agreement of what you agree on, seeing that affects the result. And in this particular case, numbers are so important that these agreements actually have become standardized, because if you don't standardize things, then different systems that are working based on different agreements for the numbers may not be compatible with each other. So for that very reason, the numbers have become standardized. One important class of numbers which become really important in a lot of precision arithmetic kind of scenarios are floating point numbers. And floating point numbers, we don't have that. Remember the fixed point number, we only could get to the certain resolution because that's how much quantization we could get out of the system. But here, the floating point numbers are very similar to decimal scientific notation that you may have seen before, where we represent a number using a fractional number, where the fractional number always has only one bit before the floating point, and all the numbers are moved to the right side of it, and then that one is times 10 to the power something. If you're talking about base 2 numbers, then this base becomes 2, of course, and but this could be the same. So this number, which is in base 10, we had 1 point, or any number. We had only one number before the floating point, and then everything went after the floating point is the same here. One thing to remember is that because we only have two possibilities, and in a number system like this, the leading zeros on the left don't mean anything. That means that the number that is to the left of that floating point is always a 1. And the way we represent this is there's a mantissa, and there is a base which is 2, and exponent which is which could be a number in a certain range that we agree on. And this is basically how we compute it. Now, as I mentioned, this is a super important topic, so these values are standardized. In the standard IEEE format for 32 bits, the first 23 bits are reserved for the mantissa. The next 8 bits are reserved for exponent, and the first bit is the sign bit. So this is the standard representation in the IEEE format. If we have 64-bit, then there is, of course, a different standardized notation, which we will discuss shortly. But what that means is that if you have an exponent and sign and mantissa, how you would represent this number in a usual format is, you first, if you're trying to represent, say, 2 to the 228 in a base 10, first, like always, we convert this decimal number to a binary, and then in the binary domain, as I mentioned earlier, we have this leading 1 point, the rest of the number, and this point is determining what is the power after the 2. So this 1 point, in this particular case, we have 1.110010 here, which means that we are doing this number if set aside. We have these 7 numbers, so this will be a 2 to the power 7, and then the zeros here don't matter, and the zeros before, as I said, don't matter. So if you want to convert this to the 32-bit number here, the exponent here is going to that 8-bit representation. So 8-bit representation of a 7 is here. So we have this exponent here. The sign bit is 0 because it's a positive number, and then the 2 to the 28 in the mantissa, we have to represent it in a 23 bits, and it starts always from the leading one here. So as you can see, the 1 1 here, and these zeros do not matter because what determines the length of the number is this exponent here, which is 8 bits. There is one optimization that is very common to do, and that is because the first bit of the mantissa is always 1. So maybe if it's always 1, which is the case for all base numbers in base 2, then we don't need to store that one additional bit. So we save 1 bit here, and that's kind of, again, part of the standard. So whenever you see a number which is in the fraction part, you know that you have to add a 1 if you want to convert it to a decimal. The fraction bits are stored in the 23-bit field, and the leading one is implied. Again, the number representations are all agreements, and because this is an IEEE standard, this is a standard agreement. But if you want to convert this, if you're writing an algorithm where you're doing these conversions by hand, then you need to be careful to always add that 1 in the fraction to your number. Now, you may think, oh, this is really a pain in the neck to do this kind of computation. But luckily, because these are all standard, there are also standard libraries that are determined. In this case, the numbers are standardized by the IEEE. So there's a standard IEEE library that is used for these type of numbers. So if you use that library, then you would be able to do these conversions. And that's something that you could get yourself familiar with if you're in need to do this floating point representation numbers. But as you could imagine, even calling the library components could help you do your operations much more rapidly in terms of coding and Verilog. But when you're implementing, we also have to take care of all the transforms that get into transforming a floating point representation into 0 and 1 digits. So that complication exists, and so the floating point numbers are typically more involved in terms of the operations that you have to do with them, like the multiplication, division, and other tasks are more overhead on them, but also you get more precision. So that's something to know when you're dealing with this type of numbers. So the one thing that is also within the IEEE representation that you may want to know about is that the exponent is never getting a negative value in that 8-bit storage format. So the exponent is computed the same way, like in the previous case, the exponent was 7. But if you're representing a 7, you have to add a bias to it, and the bias we add is 127. So if we want to represent 7 in this format, it is 134. It corresponds to 134, which is shown here. And this is again part of the standard library. It is the representation of the 228 in base 10 in the IEEE 754 32-bit floating point library becomes the sign bit, which we know, and the fraction bit, which we computed. And this 8-bit actually changes from the 7 we had before to 127 plus 7, which is 134 here. Now, again, let's represent another number in this IEEE floating point standard. The sign bit naturally should be 1. The value for this 0.25, this basically we convert this decimal number to the binary, and when converted to the binary, then we have to find a scientific representation of this, which becomes 1 point, all the numbers here, which becomes a 2 to the power 5. And now basically we could use this to fill in each field. As you see here, we don't need the leading 1, so this number becomes 1101001, as you see here, and the rest of the bits get a 0. The exponent becomes 5, so this becomes 127 plus 5, which is 132, which is represented here in the 2, and then the fraction bits here, and the sign bit is here. So this is basically a floating point standard. And there are also special cases in the standard. The number 0, because it doesn't have a sign, the sign is don't care. So when you have both exponent and fraction all zeros, then this library or this interpreter knows that this is a number 0. Plus infinity is shown by a sign 0, exponent all 1, fraction 0. So that's a plus infinity. Minus infinity, just the sign changes, the same format. And if you kind of have a non-zero fraction and all ones, then regardless of the sign, then it is used for numbers that don't exist. So if we have for example, a logarithm of a negative number or other things that are not mathematically defined, then this is how it gets represented in this IEEE library. And typically up to say 10 years ago, a lot of the processors were 32 bits. In the past decade, we've seen most of the processors moving to 64-bit notation. Of course, 32-bit is still used in a lot of embedded systems and embedded applications, so it's not that it's not used. So IEEE standard that we just discussed is in wide usage today. The double precision adds to the precision of the computing that we do. There's of course also a standard library for that in the IEEE standard, the 64-bit notation. There's 1 sign bit, 11 exponent bit, and 52 fraction bits. And the bias here is 1023. Now, floating point numbers give us a longer range to represent things. But as I mentioned in the beginning of the lecture 13, no matter what you do, you're always talking about a finite precision. Because, if you have k bits, you cannot present more than the possibilities that are, given to us by a floating point representation in the range of the exponent in the mantissa. So if we have an overflow case, that means the number is too large to be represented. If it's an underflow, that means the number is too small to be represented. And then there are rounding mode, because if you get into an overflow or you get into a precision that you don't know how to represent, you need to round it. Either you round it up or round it down, or to 0 or to the nearest integer that you have. So if we have for example, assume that I have this number, which is, this number in the fraction. And now, assume that I want to round this so it only has 3 fraction bits. Then, this would be 1.5 if I'm rounding down. It would be 1.625 if I'm rounding up. So it will be like this. If I'm rounding towards 0, that means kind of rounding down again here. It will be 1.1, and this is this is to the nearest, which again will be kind of rounding up in this simple case. So if you want to do addition for floating point, again, if you have two numbers and they have the same exponent, then addition becomes easy. You just keep the exponent out and then you just do the addition. But if we don't have the same exponent, then we have to shift one of the numbers to get to the same place. And it's usually easier to shift the smaller mantissa if necessary. So we shift these numbers so that they will become the same fraction of, like, imagine we have a number, some 1001 something times 2 to the power 5 plus some 1.00 something to the power 6. Now, if we want to put that computation to add them, we have to shift the smaller mantissa here to become a power of to become at the same power, and then we can add the mantissa and normalize and adjust the exponent if necessary if you want to go to that standardized representation and round the results. Again, the good thing is the standard library does this computation for us. Here I'm showing just the addition of this two floating point number. I'm sure you would be able to do this with the notions that we have seen. Try to do that as for yourself at home and make sure that you're comfortable. Again, this is showing how this can be done. If you're talking about the multiplication, then the exponents get added up. But you have to, when you're adding up the exponents, then you have to make sure that the exponents that we're adding up, we count for the bias. So remember, we had each of the exponents have that 127 bias. So if you're adding the two of them, if you don't subtract the 127, you will get an error. So you have to be making sure of all these. Again, the nice news is that the IEEE libraries have these functions for us, so we don't really need to think about that. It's just that you need to know that this is a standard endeavor if you're going to floating point, and conversion between floating point and fixed point has to be done before you could get good results from your programs. I hope this was helpful. We'll be continuing with our project, which is the Bitcoin function next time. Thank you.